Hi, good afternoon, guys, or good evening. So today what we're going to do is we're going to solve set of solutions for the influence line, and specifically using the Muller-Breslau principle. And so we're going to just do a series of series of problems, and just kind of go through it step by step. All right. So in this problem, it says draw the influence line moment C. Let's see where that one is. C is right there. And reaction at B. B is right there. And shear at C. So if you remember correctly, moment means that we cut that portion apart, and what we do is we apply a moment like that. Now this is pinned. I think it's pinned. Let's see. A is pinned, B is roller. Good. So that means that if we were to take that and push it up, so let's kind of redraw. Let me try as a gray line. And okay. Solve in black. So because that's pinned, what we do is at this point, we push it up like this, or rotate it up. That goes there. Now because this is pinned, right, imagine this is like a seesaw. And that essentially would create your, what is it called? And this is, so, and the amount of moment is going to be, it's going to be half a theta rotation. So pretty much what you're going to have is a magnitude of 5 there. And if I understand that correctly, it should be equal and opposite for 5 there. Okay, so that's A. And moment, we will write this as moment at C. Now reaction at B, okay, what we do is we take that member and then we're going to put an upward load to it. And again, this is free to rotate, right? So what that would look like, and maybe what I should do also is kind of draw a straight line here, okay? And we're saying at B, remember now this is a reaction, so we're going to push it up 1 unit. So that goes up. Oops. Right, and it's 0 over there. And this is 5. I mean, not 5, but this is a unity load, so that's 1. Okay, and just from similar triangles, if this is a halfway point, that would be also half. This would be 0, obviously, 0, obviously. And to kind of talk about what that means, and let's use some logic, right? If you put a sensor right here at B, right? Let's say you put a scale, a scale you have in the restroom. Let's just say you put it right there, okay? And if you were to stand right there, right at the support, your reaction would go to this column and to the ground, right? And so if you're standing at A, the question is, what would the scale read? It would read 0, correct? So that's why that is registering 0 at that point. Now, with that same principle, if you're standing right here, right? And again, we're looking at B, the scale's right here, right? So that means that whatever you weigh, let's say I'm going to weigh 150 pounds or something, right? What you'll do is that your multiplier is 1, so you take 1 times 150 is equal to 150. So essentially, that B feels 150 pounds right there, right? And taking that same logic, if we were able to stand right there, right, and I weighed 150, what that means is that I'll take 150 times a half is equal to 75, and that's what it feels right there. So remember, when we're talking about reaction at B, right, that really just, again, means that the sensor is always going to be at this point right here. And for moment at C, the sensor is always going to be placed right here. Okay? Now for, let's see, C, shear at C, assume A. Okay, so shear at C now. Now, one's reaction, remember? And so what you do is you take that support and push it up. And so when we solve for shear at C, okay, essentially, we know that its sensor is going to be placed right here. Okay. We also know that it is pinned here. I think it's like a roller or something right there. And so what you do is you break it. And so you push it down. And the other one gets pushed up. Like that. And what you want to note is that this, oops, give me my straight lines. That is 1 unit load, or unity right there. Okay, and so by similar triangles, we also know that, so this is a half. Similar triangles says that that's also a half. And that is assumed for C. That's question 6-2. All right. Okay. 6-3. Let's see what it says. Let's draw lines. Okay, so it's A, B, and C. A, B, and C. And relight line. Let's kind of do that. Do that. Let's move it over. Okay, so that kind of gives us a guideline of what we're going to do. All right, we'll go in order. And again, we're just focused on the Muller Breslau principle. Okay, so on this one, what we're looking at is vertical reaction at A. Okay. So reaction at A, here, we're taking this and we're pushing it up a unit load. So it's a reaction. So 1 unit load. Since there's nothing else anywhere else that is holding it in terms of boundary condition, right? What you'll see is that this entire thing lifts up, okay? So that entire thing is 1 unit load up. And that's vertical reaction at A. Let's draw it right there. Okay. Moment at A. Okay. So we apply a kind of a positive moment this way. And so essentially we're applying a moment and we're applying this rotation right at that point. And so essentially it's rotated that way. And because the dimension's 10 feet, this is going to be 10 times or 10 theta at that point, and it's going to be negative. Okay? And moment at A. Now the last one is shear at B. Shear at B. So what we do is we cut it at that point and we push it down, right? And that's going to be a unit load. And that's all right. Let's go on to the next question. Okay, draw influence lines at what's going on here? Let me check what it's. Okay. So what it's supposed to say is A is vertical reaction at A. So vertical at A, shear at C, and moment at C also. So again, 3 problems, 3 questions. Best thing to do, draw these lines down, draw these lines down, draw these lines. Question 1, question 2, question 3. Okay, and we said that reaction. What is going on here? Reaction at A, shear at C, moment C. A, C, C. Okay. So, reaction at A, it would mean that what we're doing is we're pushing up at A, and it's a unit low, up. So that's 1 unit load. And because this is a pin, it would look like that. And similar triangle says that that's 1, that's 1, that's 0, and that's going to be 2. Right? Because if this is 1 and that's equal distance, we know that that's going to be 2. Right? And so, again, what does that mean, right? Is that if I was to stand right here, right, and the sensor is right here, or the scale, I'll stand right here, and I weighed 150 pounds, the scale over here would read 150 times 2, so that would read 300 pounds. That's what it would mean. Okay? Okay, so shear at C. What we do is we take C and we're going to move it up. And that's going to be a 1 unit load. Okay? And that's right there. Okay? And let's look at the logic in that, right? Is that if I was standing over here, and remember where a sensor is, right? A sensor is at C right here. If I'm standing right here, this would see 0. Okay? Obviously, if I stood right at the support, right here would see 0. If I stood right here, which is again another support, this would feel 0. And because it's a cantilever, right, if I applied a load right here, theoretically this point on doesn't feel anything because all the load goes this way. Does that make sense? So let's look at it as like kind of a cantilever beam. Right, if I apply a load right here, my moment would be like that or the other way. And essentially you wouldn't have that, right? So there's no shear. Shear is equal to 0 at that point. So that's the logic in this. Okay? And some of you are saying, like, maybe asking, hey, you know, in the other problem, you know, you took it and you shifted the other side, but because there's a support here, you can't push it down, right? It doesn't, you're not going to kink it down because there's this support also, so it wouldn't work. All right, and so moment at C, again, it would mean to go ahead and break it. You break it right there, and you'd apply a unit load. Okay, so essentially, it would be, the distance is 3, so that would be 3. And you could use the same logic as that, you know, let's just say that if you're standing right here, and this is your cantilever, like this, and the sensor is right here, your moment would equal to 0, correct? So it kind of meets that logic right there. Okay. Another question that can come up is why is it this way? Why is it this way instead of that way? Right. So that's a pretty logical question. So let me let's just state what the convention is for structural analysis. If you had a member, this face, what we considered positive, would be down, out, and rotation. Okay. And then on this face right here, it would be that way, this way, and this way. The way I try to remember this is I look at this as Street Fighter. So you either choose Ryu or Ken. And if you're going to do a Shoryuken Ken, usually you're going to go forward, you're going to come down, and then you're going to go this way, and then you'll use the top buttons, not the bottom buttons. The buttons don't matter, right? The idea is that you're going to go like this, right? So that's positive. So if you know that, you look at the other side, it's equal and opposite, right? So this is going this way, this face is going that way, this is down, so that must be up, counterclockwise, so this must be clockwise, right? So know one side, which is your Street Fighter 2. I like the Championship Edition. And so if we look at this, if we cut the member, right? Remember, it's on this one we're modifying this face, which is in correlation to this face right here. Does that make sense? Because this, if we're going to cut it and then rotate this side, then it'd be this face. I know it sounds a little kind of confusing, but that's what it is. Because you're cutting this and keeping this side of the member, right? Which is essentially, if we brought it over, it would be like that. So, to simplify it, we're looking at this face, right, which is this side. And so the idea is that you do this rotation and you're rotating it down. Okay, that's the way I'd like to take a look at it. Okay, so we're good on that one. Oh, perfect. 2 more. Okay, so that's a little interesting one. Okay. Now, this is kind of like what you would expect to see on the quiz or like a midterm. And discussion is simple. It's like, it's not only that you're doing the influence line, but you're also solving for the applied load. So what does that mean? Let's go through the questions. The compound beam, compound meaning more than 2 beams, right? Subject to a uniform dead load of 1.5 kilonewtons meter and a single live load of 10. Determine maximum negative moment carried by the loads at A. So, A. Right. So what that means is moment A. B. positive shear at B. Let's see. Let's see. Oh, it's just A and B. There we go. All right, so let's go ahead and just solve it one by one. I think the best thing to always do is just kind of take it one at a time, not look at everything all at once and be like, oh no, and get overwhelmed. So what we'll do is go ahead and draw that. Oops. Okay. So moment at A, right? And so what that means is that we're going to be applying a moment that's like this, and essentially when we do that, it does this, and remember it's kinked right here, and it's going to do that back there, right? And it just essentially be theta times L, so it's just going to be 5 right here, multiplier. Great. So with that, now it's a little different because now we're actually solving for the worst case scenario load, and it's saying that you have a distributed load, uniform, 1.5, and single live load at let's see, and a single live load at, hold on, okay. So what this means is that you have a distributed load, means take the area of the entire thing. So what's the area? The area is going to be the total area because we have a distributed load throughout. So it's going to be 1/2 base times height. 1/2 base is 5 times height, plus 1/2 base is going to be 10. Height is 5. Now that is, let's see, 12.5 plus, what is that, 50, half of it is 25, so that's going to be 37.5 multiplied by the load, 1.5 kilonewtons per meter. So we know that due to the distributed load, right, that's due to the distributed load. Let me get my calculator out. It's 37.5, 1.5 times, so 56.25. Great. And then this is due to distributed load. Now point load, 10. Where does it say to apply it? Does it apply maximum or? Okay, so it's asking for the maximum, right, negative moment. So maximum means you want to apply it right here, right? So we're going to take 10 times 5. So moment is equal to 10 times 5. So we have 50 kilonewtons meters. Kilonewtons meters. Now it's saying to add those two up. So total moment, total maximum negative moment is going to be There we go. That should be it. And it's, oh yeah, negative. Question, next one is B. Okay. So what we'll do is let's extend these lines down. Let's see. Maximum positive shear at B. Okay. So point load up. Right. Now remember that I think they say it's fixed, right? A is fixed, so you can't push it up because it's fixed right here. So that means that we're gonna have something like that. And that's 1 unit load. Okay. And so that would be our diagram, and we would apply the same concept. We have a distributed load. So one is area is equal to 1 times 10 meters times half, which is equal to 5. And that's due to a distributed load, total area, right? And then we apply the 10 right here, because that's going to give us our bang for the buck. So we know that that's kilonewtons, and then we'll also do 1 unit load multiplied by 10 kilonewtons is equal to 10 kilonewtons. So we know that the total load is 15 kilonewtons. Final answer. Final answer. Is that right? 10 times half. Something is not. Let's see. Sorry, there's an error right here. That's 1.5. 1.5. 7.5. 17.5 kilonewtons. Okay. And so that's how you would solve it. You know, again, distributed load means area. Point load means, and if it's saying maximum, find it where it's where it has the most magnitude, best value, right? And that's how you solve it. So the last one, I'm not going to solve like the distributed load and all that stuff. I'm just going to solve it for the basic, and I think I count on you guys to solve for the moment and all that stuff. So the applied load moment. Kind of a very similar problem right here. Okay. First they talk about load, blah blah, being because the largest moment B. What is this? Assume that there's, okay, is it just one question? Okay, so it's just one question actually, so this is a pretty straightforward. Actually, we should be able to do this pretty fast. Okay, largest moment D. So pretty much what the question is saying is put the sensor there. At D. And this is assume A is fixed. B is pinned. C is on a roller. Right. So here, the moment there and apply it. If we were to apply it this way, let's just say we were, because this is fixed, it wouldn't rotate, right? It would stay straight because it's fixed right here. So when we do this, it's going to kink it down and it's going to go back up to that point, and we know it's a unit theta, so theta 8, so this is a 8. And if it's 500, really moment max is equal to 8 times 500, so that's 4,000 pounds. Final answer, pounds foot. There you go. All right, hope this helps. If you have any questions, let me know.